Well, but by only keeping t extra.
Oh yeah, okay, sorry. Now I understand what you mean. So you have the input bits, you have the answer. So that's kind of the minimum number of bits that you need to make it reversible. But that's not a, I mean, if it's a big complicated function that you're computing, you can't just say, oh, that's what I want to do, because that's like invoking magic that I just want to get the answer, right? So you have to build up any computation you want to make out of smaller parts that you definitely know how to do. I mean, this is actually a real problem because there's some functions that not only are hard to compute, but that in general cannot be computed. That there's no algorithm that will solve, for instance, the halting problem. Given a program, does it halt in a finite amount of time or not? There's no algorithm that will solve that. So you can write down a function that gives that answer, but there's no way to tell what that answer is. So just kind of saying, oh, yes, I want to write down the answer, that's not good enough. You actually have to be able to build it out of something. OK? Any other questions? So that actually ties into what I wanted to start with today, which is universal gate sets. So I said some of this already yesterday. So yesterday I introduced to you a bunch of kind of basic gates, basic building blocks that you can use to make quantum circuits or classical circuits. But then the question is, can you put those together to do anything you want? OK? So that's the basic notion of a universal gate set, is a set of gates which by themselves are enough that you can put them together to solve any problem that can be solved. So in particular for classical systems, a universal gate set is a set of gates that can be used to compute any function. So you might have n bits of input, and you want to compute some arbitrary function of those bits. And the universal gate set is one that will allow you to compute any such function. Okay. So that may sound in contradiction to what I just said, that there's some functions that can't be computed. And the reason for the difference is that in this version, I'm saying, let's fix the number of bits. And then I want to compute any function on those bits. Whereas the example of the halting problem was a case where the input could be any program. So it could be arbitrarily long. But for universal gate set, it could work for every n. So the thing is that for any fixed n, you can always compute this function if you know what it is, which is the hard part of the halting problem. But as n gets arbitrarily large, the algorithm you might need to figure out what this thing is could be very unpredictable. We'll talk more about that later. Anyway, so the idea is we have this function, or we have a kind of an arbitrary function. We want to build it up out of these fundamental gates. And usually we're going to stick to universal gate sets that act on just a few bits or a few qubits. Okay, so like all the example gates I showed you yesterday acted on 1, 2, or 3 bits or qubits. And using that, we're still going to build functions that act on many, many bits. Okay. So anyway, let's. I'm not going to give you the detailed proofs that these constructions, that these gate sets are universal. But let me just at least write down some example sets. So for irreversible classical computation, I mentioned yesterday that and and not are universal. And maybe one way to see this is that, well, if you fiddle around a bit, you can see that and not can do the exclusive OR. The exclusive OR it does like a binary addition. Okay? And the AND does multiplication for binary numbers. And if you think even harder, you'll see that an arbitrary function on n bits can be written as some polynomial, possibly of a high degree, of these n bits. I guess the degree is kind of limited to n, because binary number is x squared. xi squared is just going to be xi. But you could have a degree n, and you could have any subset of the terms. So it could have 2 to the n possible terms here. And so any function can be written as a polynomial, and then you can build that up out of addition and multiplication. Okay, so that's why this is sufficient. You didn't have to understand that argument. I just wanted to say something to give you an idea of how this works. But then, of course, if we want to do reversible classical computation, this is not good enough because, because AND is not a reversible gate. So for reversible computation, the Toffoli gate, as well as the ability to create ancillas in either the 0 or the 1 state. Well, this is not really a gate, but I'm just putting it down there because it's an essential part of the construction. But then the Toffoli gate by itself, as I mentioned yesterday, is enough to give you both and not using the appropriate inputs for some of the bits. Okay? And therefore, this set of gates is also universal. Okay?
Why do you include the ancillas among the gates?
Well, I mean, it's kind of arbitrary. So normally when people talk about this, they wouldn't include that because it's not really a gate in the usual classical sense. I'm including it just to remind you that you have to have that capability. If you can only create 0 ancillas, which is kind of another sensible default thing, then the Toffoli gate by itself is not enough, because you can't do not. So the ability to create 1 ancillas is a little bit non-trivial. It's not necessarily very hard. I mean, particularly with classical bits, but it's a capability that you need. Okay, and this becomes more of an issue in the quantum case, where there is some very non-trivial ancillas that become important. Okay, any other questions? Okay, so now let's move to the quantum case, which is, of course, what we're really interested in. So what does it mean to have a universal set of gates quantum mechanically? So it's no longer true that we want to just compute some straightforward function like this. Instead, what we want to do is we have n qubits, and we want to do an arbitrary unitary transformation on those n qubits. So in the quantum case, a set of gates is universal and produce any unitary gate, any unitary operation. Of course, one thing about quantum gates is that, as we mentioned yesterday, the global phase has no physical significance. So suppose all your gates lie in SU, well, SU2 is not going to be enough, SU4, say. Okay, so you have 2 qubit gates with determinant 1. They're all unitary. And maybe getting them multiplied together, you can get any gate in SU2 to the n. Okay? So that actually would be sufficient, even though you don't get any unitary operation, because you get any unitary operation up to a global phase. So we could, for instance, take u to be an SU2 to the n. An SU2 to the n is the right thing for an n qubit unitary is going to have, remember, n qubits is a 2 to the n dimensional Hilbert space. And so u2 to the n or SU2 to the n is the unitaries that act on that Hilbert space. Okay? So what are universal sets of gates? So there's a couple of different sets that are kind of commonly used. So one of the most common is controlled knot plus arbitrary single qubit unitaries. So single qubit unitaries include both of the gates I talked about yesterday, the Hadamard and the R theta phase rotation gate, but also lots of other single qubit unitaries. You can rotate around some other axis. You can do, well, basically reflections. I guess that's included in the phase rotation. So with complex, it's more, anyway. So anyway, so single qubit unitaries, basically they form SU2. But then you have to have something that interacts different qubits. And it turns out it's sufficient to have just one, for instance, the C naught. Putting that together, you get a universal set of gates. Yeah?
How many single qubit unitaries do you need?
Well, so this particular set is all single qubit unitaries.
Right.
Okay? So that's an infinite number.
Right.
So it turns out we don't really need them all, but let me get back to that in a second. So anyway, so let me just point out one thing, which is that whereas for reversible classical computation, you needed the Toffoli gate, which is a 3-bit gate. And actually, it turns out there's no set of reversible classical universal gates that uses only 2-bit gates. The quantum case, they're also reversible, but it's sufficient to have only 2-qubit gates. And so in particular, if you think about this, that means that the Toffoli gate classically cannot be built out of 2-bit classical reversible gates. But the Toffoli gate is also a valid quantum gate. And it can be built out of just 2-qubit quantum gates. And you might get that on a homework problem. We're working on that. Anyway, the circuit is not too complicated to do that, but we'll see whether we force you to figure it out yourself or otherwise give you some assignment relating to that. OK, so this is a universal set of gates, but again, it's not all that great because it's an infinite set of gates. So for a lot of purposes, it's good to have just a finite set of gates. But when you think about it, there's an immediate problem you run into. So the problem is that SU2 to the n, the thing that you're trying to get, is an infinite set of gates. And if you take any finite set of gates and you take products of those finite set of gates, well, you'll get a finite set. And more to the point, even if you take arbitrarily long products, you'll get a countable set of gates. So that's the cardinality of the integers. But SU2 to the n that's the cardinality of the reals. It's uncountable. Okay, so that immediately tells you that it's not possible to get exactly every unitary gate using just a finite gate set to start with. Okay, but luckily we don't really need to get exactly every unitary. We only need to get approximately every unitary. And it turns out that finite gate sets are enough to do that. So let's say a gate set is approximately universal. If it can get arbitrarily close to any unitary. So in other words, it generates a dense set. Okay. So for any unitary, you pick an epsilon. You say, I want to get epsilon close to that unitary. And then there's going to be some product of gates from the universal set that will get you at least within a distance epsilon from that unitary. OK, so what are examples of some gate sets that do this? Well, so one of them is 3 of the gates we saw yesterday. Actually, both of them are sets we saw yesterday. So if you take the Hadamard, the pi/4 phase rotation, and the Toffoli gate, that's universal in this sense. If you take the Hadamard, the pi/8 phase rotation, and the controlled knot, that's also universal in this sense. Okay. And of course, you can come up with lots of other sets of universal gates, either exactly or approximately universal. Okay? Yeah?
Is it to prove that these are approximately linear?
For these particular sets, I mean, it depends what you consider easy, I guess. It's not a super advanced thing. You just have to do a bunch of calculations. But it can get a bit long, because you have to say, well, OK, so for instance, I can put h and r⁴ together in various ways to get arbitrary single qubit gate, arbitrary close. And then once I do that, then I have to say, well, single qubit plus C0 are universal. This is maybe a little more complicated because you have to go up to 2 or 3 qubits to start with, because these are not, by themselves, are not enough to generate single qubit gates. And I mean, you know, there's various stepping stones along the way. You say you can get, well, this set of gates, and then you go from here to get this other set of gates. And it's not, none of those steps is by itself really hard, but going through them, the whole thing can take a few pages at least. Any other questions? OK. So one thing I should point out before I go on is that just because you can get a unitary using this basic set of gates doesn't mean you can get it very quickly. So this is already true in the classical case. If you want to get this kind of an arbitrary function of n bits, well, in general, it might take 2 to the n of the basic gates. Okay? And you have this kind of similar situation in the quantum case, where you could have exponentially many of the basic gates needed to get the unitary that you want. Remember, of course, when it's approximately unitary, well, then there's also the precision that you need, right? So to get arbitrarily good precision, well, you could need more and more and more gates, right? So it's kind of an unbounded number of the fundamental gates. And we'll talk on Friday and next week about kind of the notion of what it means to efficiently compute a function. And that means we need to get a notion stronger than just universality. We want to be able to do it in a reasonable number of gates. Okay, so that's just giving a preview of what's ahead. OK, so now I want to move on to a slightly different topic, which is, well, so we have these quantum gates, so what can we do with them? And I just want to show one particular example, which is something those of you who've taken the foundations class will already have seen this. It's quantum teleportation. So in quantum teleportation, there's two people, Alice and Bob. And Alice wants to send a qubit to Bob. Okay. Now, we'll talk tomorrow and Thursday about different ways to implement quantum computers. But let's just imagine, for instance, that Alice has no direct quantum connection to Bob. Okay. So she can send classical bits to Bob, because that's easy. She can call Bob up on the phone. But moving qubits around, that might be harder, okay? Because you have to preserve quantum coherence, and that can be a very delicate thing. Luckily, Alice and Bob have been in close contact sometime in the past. And so they do share some quantum resource. They share an entangled state. And so in particular, they share the state 0, 0 plus 1, 1. Okay? And we saw last time that they can create this state. Make it a circuit. They can create this state by starting off with 2 0 qubits, and then doing the Hadamard on one of them, and the controlled knot from one to the other. Okay? But Alice is going to keep one of these qubits, and Bob is going to keep the other one. So in order to do this controlled knot, presumably they had to do it sometime when they were physically in the same place. Okay? But then, once they've done that, they go off in opposite directions. Sometimes you might say they get in spaceships and travel in the opposite direction. So they're very far apart now. And so Alice is up here. Bob is down here. And while they're out exploring in their spaceships, Alice encounters an interesting qubit that she wants to send to Bob. So this qubit will say have the state psi. And like I said, Alice cannot directly send the qubits, but she can still communicate with Bob classically. And so quantum teleportation is a way that she can get the qubit to Bob. And that's a little bit surprising if you think about it, because, well, this state psi, certainly Alice, if she was to measure this state, she couldn't possibly get all the information out of psi that she wanted. She couldn't get a complete description of psi, right? That's prevented by the uncertainty principle. So that would be maybe the first thing you might think of. She measures psi, she figures out what it is, and then she sends that classical information to Bob. And then Bob can reconstruct the state in his own lab. But that's certainly not going to work. So how is it possible that Alice can send this? Well, this is where the entangled state comes in. So Alice is going to do a joint measurement on her state psi and the qubit from this entangled pair. And in particular, what she does is a Bell measurement. So that can be implemented using more or less the inverse of this state creation. And then she has two qubits, one from the EPR pair, one from the state that she found. And so she measures both of them after this little circuit. And so she gets two classical bits. And she sends those classical bits to Bob. And then based on the two classical bits that Bob receives from Alice, Bob does some unitary, which is one of the identity or one of the Pauli matrices. And as a consequence of that, Bob gets back the original state psi. And I don't mean he gets back psi approximately or with high probability or anything. He gets back exactly psi. Okay? So somehow, even though there was no possible way Alice could measure all the information inside, she still got it to Bob. And in fact, these two classical bits are random. They have the classical bits by themselves have no information at all about psi. So if some third party comes along and listens into this transmission, they won't be able to get any information about psi at all. And actually, that had to be the case, right? Because the no-cloning theorem says you can't make a copy of psi. And, well, there's no copy here because Alice destroys it when she makes this measurement. And nobody else can reconstruct it from the classical bits. But Bob, who has the other half of the EPR pair, that's a unique thing. He can put that together with the classical bits and get back psi. Even though the EPR qubit by itself has no information about psi, right? It can't because they made it before Alice even found psi. Okay? So I don't really want to go through the math to show that this works. It's not too hard. You can do it yourself if you want. And I think if you took foundations course, you probably already did do it yourself. Quantum teleportation is kind of an example of a simple quantum information protocol, one of the first quantum information protocols known. And it's conceptually interesting, but it's also practically useful. Again, I don't want to get into too much detail here. But in the realm of quantum information, well, it's useful for, well, the example I gave with the spaceships and exploring is maybe a little bit silly. But in practice, there's a lot of situations where you do have one qubit, and you want to send it somewhere else. Okay? And sometimes you can do that just directly by, you can store the qubit as a photon, and you can send it through an optical fiber. But over very long distances, that's not going to work very well. And there's other situations where the qubit is maybe not stored in a photon. It's some other type of system. And you still want to send it. And quantum teleportation comes in very handy here. Basically, what you're doing is you're kind of separating the task of quantum communication into two subtasks, which are potentially simpler. One of them is classical communication, and the other is this shared entangled state. Okay. And so this when you're sending qubits, it could be long distances. It could be, from Waterloo to Vienna or something like that. Or I guess Innsbruck is more likely. There's quantum computing people in Vienna, but there's even more in Innsbruck, so in Austria. Never mind. Or you could be sending it very short distances. Like you have some quantum computer, and there's a qubit over here, scaled up a lot. So you have quantum computer might be very, very small, but you have a qubit on one side of the computer, and you want to send it to the other side of the computer. Okay, and quantum teleportation can be useful for that even. And quantum teleportation is also useful as a building block for more complicated protocols. So for instance, there's various ways to modify quantum teleportation or use related protocols to quantum teleportation to do computations beyond just sending the qubit. And in that case, you don't really care that Alice and Bob are in separate locations. They can be right next to each other. But the fact of teleporting the state through some appropriate ancilla can then perform a gate instead of just moving it from one place to the other. So it's kind of a nice building block, both conceptually and practically, to work in quantum information. Plus, we're getting started. I wanted to show you something that you can do with these gates. OK? Are there questions on that? Yeah.
So what else do we need to have a universal quantum protocol?
What do you mean?
Using this quantum teleportation, what else do we need to?
Oh. Let's say, suppose you can create arbitrary ancillas here. And that might be even more than 2 qubit ancillas. You could have to use, say, 4 qubit ancillas. And you can teleport states through these ancillas. And then to do the teleportation, you need Bell measurement and single qubit operations, pretty much. That should be sufficient. If you look in more detail at exactly what gates you can do, then you can narrow down exactly what single qubit operations you need as well, and exactly what ancillas you need. There's multiple choices. OK, other questions? OK. So then I want to get back kind of to the notion of universality. And let's think again about what we said. So I said that we want to be able to do some arbitrary unitary transformation on the Hilbert space. But is a unitary transformation really the most general thing we can do? We really want to do the arbitrary thing that's allowed under quantum mechanics. And are unitaries enough, or are there more things that are allowed by quantum mechanics that this set of gates won't give us? So most generally, unitary is the most general thing that will map pure states to pure states. But quantum mechanics also allows mixed states. So we should, in general, allow any operation that maps density matrices to density matrices. Okay? So what is the most general operation that maps density matrices to density matrices? Well, certainly if you have a unitary, that works. So if a unitary U applied to a density matrix, rho, it will map it to U, rho, U dagger. And U, rho, U dagger will again be a density matrix. OK, so that's good. That's the consistency. But you can do things that won't necessarily be unitary. So for instance, it's perfectly valid to have a quantum operation that takes an arbitrary qubit and throws it away and replaces it with a 0 state. that's physically allowed. The new state, well, it's always the same, but it's still a valid density matrix. Okay? And then there's lots of other things you can do. So what properties should such an operation have? So first of all, it should be linear. And when I say linear, I mean linear on density matrices. Which is not quite the same as linear on Hilbert space, although it's very closely related. So in particular, so if we have some operation S, then S of P rho 1 plus 1 minus P rho 2 should be equal to P S of rho 1 plus 1 minus P S of rho 2. So why is that? Well, this thing here, P rho 1 plus 1 minus P rho 2, is a mixture, probabilistic mixture, of density matrix rho 1 with probability P1 and density matrix rho 2 with probability, with rho 1 with probability P and rho 2 with probability 1 minus P. Okay? And, well, so if we have rho 1, then the operation we should get after S, the density matrix we should get after doing S should be S of rho 1. Right? And that's still true with probability P. And then if we started with rho 2, then after doing S, we should have S of rho 2. And that happens with probability 1 minus P. So that means that the output is, well, with probability P, it's S of rho 1. And with probability 1 minus P, it's S of rho 2. So that's this density matrix. OK? So S has to be linear. So let's see what else. So S should preserve the trace. So if you have something that starts with trace 1, so that means the total probability of something happening when you make a measurement is 1. Well, the density matrix Cn should also have trace 1. This is to conserve probability. So trace of S of rho is equal to trace of rho, which usually is going to be 1, but it would also apply to non-normalized density matrices. So what else? Well, density matrices are positive matrices, right? All the eigenvalues are non-negative. So that means that S should take a positive matrix into a positive matrix. Because we don't want to, if we got S of rho had a negative eigenvalue, that would correspond somehow to a negative probability, whatever that would mean. So that's not allowed. So S should be positive, which means that if rho is greater than or equal to 0, then S of rho is greater than or equal to 0. OK? So this seems like it covers all the bases, right? Because what is a density matrix? Well, it's Hermitian, it's positive, it has trace 1. And that's enough to say that you have a density matrix if it satisfies those conditions. And so we have conditions that kind of correspond to all of that. But it turns out this isn't quite enough. We need something else, which is called complete positivity. Okay, and complete positivity means that it's not just enough that S should be positive when applied to a single system, but it should also be positive when you apply it to part of an entangled system. So in particular, this means that S tensor the identity should be positive. it turns out, I mean, this could be true for any Hilbert space that you're tensoring with. But it turns out it's sufficient to consider this for arbitrary states of Hilbert space that's the same size as the original one. Okay, and that's because that's kind of that kind of gets all the possible entanglement you can have. Okay, and so what this means is that you have to say, well, like I said, S should still be positive applied to parts of an entangled state. Part of an entangled state. Okay? So I'm going to say more about characterizing these maps that have these properties in a minute. But so far, do people have questions about these conditions?
Well, whatever we have is a density matrix, right?
Mm-hmm.
So what does it mean to define these properties? Right? Because whatever we do with a qubit, then we would end up with a...
Yeah, so these are properties on a map S. And I'm claiming that in order to be a possible physical operation, something that's allowed by quantum mechanics, S should have these properties. Because if it doesn't have these properties, there's some state that you can put as the input that's a valid quantum state that will give you something as the output that's not a valid quantum state. Okay?
And something else. Is that positive greater or equal than 0, or is it greater than 0?
Greater than or equal to 0. So for some reason, this is called positive when you apply it to matrices like this. But it's really, in some sense, it's non-negative. Rho, of course, is a matrix. So saying that rho is greater than or equal to 0 as a matrix means that all the eigenvalues are non-negative. But you certainly could have 0 eigenvalues, right? Like a pure state has 0 eigenvalues. Other questions? Okay. So it turns out that these so completely positive implies positive, of course, because, well, you could just apply it to a non-entangled state as well. This one is, the linearity is kind of taken for granted. Trace preserving is important too. So usually we refer to these as completely positive trace preserving maps. Or CPTP for short. Sometimes you can get away without the trace preserving if you do an operation and involves a measurement, and you say, well, on one measurement outcome, I'll keep the answer, and the other measurement outcome, I'll throw it away. Then sometimes you treat that as a non-trace preserving map to take into account the probability that you got the answer that you threw away. Okay, so the part of the trace that's there is the answer that you keep, and the part of the trace that's missing is the other outcome. Okay, but you can always think of such things as kind of incomplete CP-TP maps, where there's some extra thing that you're ignoring. Okay. So this it turns out is the most general quantum operation. If you took a foundations class, you'd also probably have seen the most general measurement that you can do, which is called the POVM. And so the POVM, which stands for positive operator valued measure, is some set of operators EI. Each EI is positive. And the sum of the EIs is the identity. And then what this means is that you have a bunch of possible outcomes indexed by I. And outcome I occurs with probability trace EI row. When you probability when you measure the state row. Okay? And looking at this formula, you can see why you need these conditions. You need this one so that the probability is greater than or equal to 0. And you need this one so that the probability is sum to 1. Okay? So I'm not really going to use POVMs much. I'm actually not really going to use CP-TP maps all that much. But it's a good thing to know about these things. Okay? So back to universality. So if we have a bunch of gates that let us do an arbitrary unitary, why do I say that's universal? Because it doesn't let us do, at least not obvious, how that lets us do an arbitrary CP-TP map. Okay? The reason it's really enough is because of a notion called purification. So this whole approach is sometimes known by the slightly humorous name Church of the Larger Hilbert Space. So the Church of the Larger Hilbert Space teaches, as, well, kind of a religious article of faith, but also something that's backed up by strong mathematics, that despite having these general operations where you have a density matrix and CP-TP maps and POVMs, that everything can be viewed in a larger Hilbert space as something unitary or as a projective measurement acting on a pure state. And so what's the mathematics that backs that up and lets you do that? Well, it's a series of theorems. So the first theorem says any density matrix can be purified. So what does that mean precisely? Well, that means that for any density matrix rho acting on the Hilbert space A, there exists a pure state psi acting on joint Hilbert space AB such that rho is equal to the trace over B of psi. Okay? So this is the theorem that says, well, in the Church of the Larger Hilbert space, there's no distinction between proper and improper mixtures. Even if it's really, in some, really is a notion that is rejected by this religion. Even if it's really an improper mixture, it was formed somehow by randomly choosing different possible states, well, you can still view it as an improper mixture, one that's formed by taking a pure state and throwing part of it away. Okay? So that tells you that the states can be thought of as pure. What about measurements? So another theorem says that any POVM can be purified. And so what that means in the case of a POVM is that for any any P over M you're given, there exists unitary U and some projective measurement, the standard von Neumann measurement, such that this circuit with an appropriate number of spots, so you have put in rho on some qubits, you put in 0 ancillas on other qubits, you do the unitary U, and then you make some measurement. And this is equal to the P over N. Okay. So the precise details of how I've drawn this, where you're measuring all the qubits, it may not break up so easily into qubits, this P over N. So there may be some little bit of additional information here that you have to kind of ignore to get this P over M. But basically, this is just a statement that you can implement the P over M using unitaries and then regular projective measurement, with maybe a little bit of classical post-processing of the information to put the answers in the same form. Okay? Okay, so that takes care of the states and the measurements. What about the operations? So I'm going to combine the theorem that says that completely positive trace-preserving maps can be purified with another theorem characterizing CP-TP maps. And so I will say this. The following are equivalent. So A, S is a CP-TP map. So B, S of rho can be written sum over K, AK rho, AK dagger, with some AK dagger, AK equals I. So the order reverses here. It's AK on the left and AK dagger on the right here. But in this sum, it's AK dagger, AK. And this condition is what gives you trace preserving, basically. So this thing is called the Krauss representation. So the AKs can be basically any matrix. It doesn't even have to be square matrices. Because CP-TP maps, they don't have to map you from Hilbert space to the same Hilbert space. They can map you to Hilbert space of different size. So for instance, I gave the example where you take a qubit, you throw it away, and you replace it by a 0 qubit. Well, it's perfectly valid also to have something that has an input state that's 10 qubits. And you throw it away and replace it by a single 0 qubit. That's a valid CP-TP map also. And there, the input Hilbert space was dimension 2 to the 10, and the output Hilbert space is only dimension 2. You're not even using all of that. Okay, so these AKs can be non-positive. They can be non-square. But this combination AK dagger AK is always going to be positive. And so that's kind of where you get the positivity from as well, because you have both the AK and the AK dagger here. Okay? And then, of course, the third condition is the one that says S can be purified. So there exists some, well, the ancilla can be all zeros, and some unitary U such that U purifies S. And so this is called the Stein spring dilation. And what that looks like is, again, a circuit where you have the input rho and some ancilla, which we can assume is 0. We do the unitary. And then up here we have the output, S of rho. And here we have another output that we simply throw away. Okay? And again, this output here doesn't have to be the same dimension as this, so that this thing here doesn't have to be the same dimension as this. So it's perfectly fine to have no ancilla here. That's still a valid. I mean, it's not possible for every CPT map, but there'll be some that you don't need any ancilla here, but you might still want to throw something out. There's others where you don't want to throw anything out. You want to keep everything, but you still have some ancilla, so the Hilbert space gets bigger. And then, of course, there's plenty where you both add an ancilla and you throw stuff away. But again, they don't have to be the same size. Okay? And so what this tells us is that getting a universal set of gates that does arbitrary unitaries, that's good enough. Because, well, adding ancillas, we've kind of already assumed that. And throwing qubits away, well, that seems like something we should get for free. You know, doing lots of stuff on qubits is very difficult. But ignoring qubits, that's not so hard. Okay? So there are questions on this. Yeah?
Why is it called a dilation?
So it's a dilation basically because you're kind of embedding you're embedding this CPTP map into an action on a larger Hilbert space. So that's yeah, I guess it's the Hilbert space that's being dilated there, something like that. I'm not sure of the exact historical source of the name. Any other questions? Okay, one more point I want to make. So these purifications, all of these purifications for density matrices, for POVMs, and for CPTP maps, they're not unique. Okay, when you purify a density matrix, you get some bigger unitary. So you have this composite system now, AB, and if you do any kind of unitary on B, well, you get a different quantum state, potentially, but it will still purify rho, because you haven't touched system A at all. Okay, and that turns out to be exactly the freedom that you have to choose the purification. Well, there's also some freedom of the Hilbert space B. But basically, it's unitary freedom on B. And similarly, POVM is not a unique, unitary. For the CPTP maps, again, not a unique unitary. Also, this Krauss representation is not unique. Okay, so there can be more than one, and generally there is. I mean, if it's non-unitary, even if it's unitary, it's kind of trivial then. But in general, there's more than one Krauss representation of a CPTP map. In much the same way that if you have a mixed state, there's more than one decomposition of that as a mixture of pure states. Okay, let me very quickly do a simple example of CPTP maps so you can kind of see some of these things at work. And then that will be it for today. And so the example is phase damping. So suppose you have a single qubit, and you write the density matrix something like ABCD. Then complete phase damping will get rid of the off-diagonal density matrix elements. So it'll take ABCD to A00D. Okay? It's probably the easiest thing to see is that this is trace preserving, right? Because the diagonal elements to stay the same. But it's also positive and completely positive. So let's try writing it in terms of its Krauss representation and the sign spring dilation. OK, so the Krauss representation, well, there's one obvious Krauss representation. Which is basically what we're doing is we're kind of doing a measurement here of whether it's 0 or 1. OK, that will also kill the off-diagonal density matrix elements. So what we can do is we can let A0 be the projection on 0, and A1 be the projection on 1. OK? And if you think about it, you'll see that A0 row, A0 dagger, well, it projects on 0, so that gives us A in the upper left-hand corner. And A1 row, A1 dagger, will give us D in the lower right-hand corner. So that's certainly a possible Krauss representation. And that's another way of seeing that this is a CP-TP map, because it means it satisfies B. And anything that satisfies B is going to be a CP-TP map, because these are equivalent. There's also other Krauss representations. So one that's nice is you can let A0 prime be the identity, and A1 prime be sigma z. So I'll just write that as a matrix. So 1/2, I guess, has to be 1 over root 2. OK? And it's not nearly as obvious, but this does exactly the same map, this phase damping map. And kind of the way you can understand that is this matrix here will flip the signs of the off-diagonal elements. And so when you add up the effect of this with the effect of this, well, the diagonal elements, they stay the same for both of them. So they end up as the same. And these things cancel out between this part and this part. You can do the calculation yourself. You'll see that it works. And then there's the sign spring dilation of this map. And remember, I said this is basically kind of like a measurement. So that's how we can implement it. We can take the density matrix rho, we add an ancilla 0, and we do a controlled knot. And you see, if this state started out as a 0, then this ancilla stays as 0. If this thing started out as a 1, then the ancilla becomes a 1. Okay? And then we throw away the ancilla. Okay? And so this is kind of like the situation yesterday where we had the extra scratch bit and we didn't erase it. It destroys the coherence between the two things that are separated by this measurement. Okay? So again, if you write it down and work it out, you'll see that this purification does, in fact, give you this map.
So the throwing away, by that you mean tracing over a degree of freedom?
Mathematically, that's what it means, yeah. Physically, it means just not using that qubit again. Or even literally throwing it away. That's a good way of ensuring you don't use it again. OK? OK, so that's it for today. The tutorial today will give you some chance to practice with this stuff. OK?